Alrighty, so Algebra 2, Lesson 2.7, absolute value functions, graphing those, and we want to be able to graph them, but let's find our little yellow sheet because we should do our little grading before the lesson. And 2.6 and 2.7, as I talked about on last week's video, those are lumped together. It says I can apply translations of functions both graphically and algebraically. So that's kind of a wide open thing. And it is going to cover our absolute value functions as well. So you probably already rated yourself on that before you started doing 2.6. Today, absolute value functions. What we need to know is the same thing that we've had to know about any group of functions. What does the parent function look like? And what does the most basic one of these look like? And then we can just add little features to it. So the absolute value function is just f of x equals, and then you've got some absolute value bars and an x. Well, it doesn't look too big and scary. And that's the biggie. It's V-shaped. Absolute value functions are V-shaped graphs. So it says it's symmetric about a vertical line, this one you learned about in the G word, geometry, axis of symmetry. So it's a big V that if you folded it down the middle and you opened it up, you get the exact same thing on both sides. And that's what's going on. It has a single maximum point or a single minimum point because it's a V. Either it's got a dot up at the top that's the maximum, or it's got a dot down below that's the minimum. It all depends on which way it's going to open up. Now that point is called the vertex. We're going to love that point because that's going to be the point that we start at whenever we do our graphing. And then we're going to use something we already know how to do. We're going to use slope. So once we have the vertex, we'll use slope to figure out what the right half of the V is going to look like. And then we'll use the opposite slope to get the second part of the V. So the slope of the left branch. Now right now they're telling us just use a slope of 1 because this is just for the parent function. So when we say f of x equals the absolute value of x, there is an imaginary, I'll do the fancy 1 there so when people look at the notes they'll go, oh yeah, that's really a 1. There's an imaginary 1 in front of it. And that's the slope of the right side of the graph. So if we find the vertex, then we're going to go up 1 and over 1. Do that a couple of times so we can get ourselves a nice half of a V. And then we'll use it backwards for the other side. And we'll have a nice V shape to it. So all of our graphs for absolute value should look like big V's, like this blue over here. And yes, you could make tables, but quite frankly, we don't need the stinking tables. We won't need them. We're going to be using vertex and slope, and we're going to say goodbye to tables when we graph absolute value. Now this is going to look a little weird for you right here. That is the absolute value function broken into pieces. When we do that, that's called a piecewise function. And so what's happened here is they're saying, hey, if you put in 0 or positive numbers, you just get the number that you had. It comes right back out. That makes sense. The absolute value of 3 is 3. The absolute value of 5 is 5. And this one says if you put a negative in here, it's going to come out the opposite. So if you put in a negative 4, you're going to get a positive 4 because absolute value is distance, so it's going to be positive. So absolute value of 1 is 1. Absolute value of 2 is 2. Absolute value of 3 is 3. Absolute value of 4 is 4. There's the right portion of the graph. We're not going to do the table. We're going to say, hey, it starts at 0, 0, and its slope is a 1. So up 1 and over 1, up 1 and over 1, up 1 and over 1. And then we'll do the other side by saying, well, now I'll go up 1 and back 1, up 1 and back 1, up 1 and back 1. And then we won't need to have tables for all of these. So this says, what is the graph of the absolute value function, y equals the absolute value of x minus 4? How is this graph different from the graph of the parent function, f of x equals the absolute value of x? And to do that, I want to remind everybody about the A, H, and K stuff that we started talking about in 2.6. Now for absolute value functions, a is actually going to be the slope of the right side of the graph. So the right side of the v. H, which has to be inside the absolute value bars, H is going to tell us whether or not we should move it right or left. But the thing with that is, it's with the X. And like I said on the 2.6 videos, anything with the X is always the opposite of what we think it should be. So H is going to be right or left. K, that's the number that hangs out in the back. And that one's normal. Plus is up and minus is down. We like that one. That one makes sense. It's just everything with the X that's the opposite of what we see. So this one says, how is this graph different from the parent function? Well, I want to start with the parent function. Our normal absolute value graph starts at 0, 0. And the right side of the graph has a slope of 1. So we're going to go up 1 and right 1. And we're going to make dots. I'm going to do that a couple of times because I'm really crummy at drawing straight lines up here on the smartboard. So now I can connect all those up, but I realize I need the other part of the V. Oh, here, make this one dashed. I should have just stopped at my dots. I was thinking I want to do dashed, and then what I didn't do was draw it dashed. But you could just leave it with dots for now, too. Now, we do that slope backwards for the left side. So up 1 and left 1. Up 1 and left 1. It's just a perfect V. Now here's the reason I want to leave that one dotted or dashed. That's not the one they want me to graph. That's the parent. They want me to graph this one. And if you have a different color, please have that different color out so you can tell which one was which when we went through these. So I'm just going to color code this. This one will be blue. You ready? Here's what we're going to do. We're going to figure out what this -4 does to this graph, and then we're just going to move it. That's all we're going to do. So I look up here, and I see, well, it's not with the X. It's in the back, all by itself. Oh, well, that's the up and downs, and those are normal. So if it's a -4, I just need to move that graph down 4. That's all I have to do. Move the graph down 4. I don't know about you, I'd much rather count to 4 than make a table. And that's what we're doing. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. Done. Nothing fancy. So everything was the same except it had a -4 in the back. So all we had to do was count 4 units down, and this one we make solid, because in mathematics, if you have a dashed or a dotted line, that means it's just a helper. But the solid ones, those are your answers. There it is. So let's see, what did they want from us? They said, what is the graph of the absolute value of y equals the absolute value of x minus 4? We just graphed that. How is this graph different from the graph of the parent function? Translated 4 units down. That's how it's different. Looks exactly the same. We just slide it 4 units down. How we do? Cool. Hope they're all that easy. Well, let's try this one. Well, this must be harder. What is the graph of y equals the absolute value of x plus 2? So I'm going to start with the same parent. And I'm going to color code. So my red one is going to be my parent. Starts at 0, 0. Up 1 and right 1, up 1 and right 1. And then up 1 and left 1. Lots of times. Let's answer the second question first, and then we'll be able to graph this really quickly. How is the graph different from the parent function? Translated 2 units up. That's it. So all we have to do is be able to count to 2. I'm pretty sure we can all do that. We'll move our little vertex up 2, and we'll pick a couple of spots on the graph and move them up 2 and make that one solid. You hoping they're all like this? No? Yeah, yeah. Now, the only thing that would make that a little more complicated is if our slope isn't 1 anymore. But even that's not tough because we've studied slope before. And we know if we get a 3 for a slope, we'll just go up 3 and over 1 instead of 1 and 1. So, yeah, they're going to change it a little bit, but it's still going to be pretty basic, right? It really is. So, this says we need to remember all those little transformations that were in 2.6. And they also are going to apply to, they will work for absolute value functions. Absolutely will. And that's what I was showing you much earlier when I wrote y equals a, absolute value of x minus h plus k. Where the big sticker is, and this is just something maybe 2 or 3 people forget in every class when we take the test. If it's in there with the x, think opposites, because x always makes everything the opposite of what we're doing. So here's what this says. If you have that up and down, that vertical translation, you just look for the number that's hanging out and back. If it's a plus, it goes up. If it's a minus, it goes down. Very logical, makes perfect sense. But like I said, with the horizontal translations, this is where you have to kind of think opposites. So if it says minus 3, you're actually going to go 3 to the right. And if it says plus 7, that means you're actually going to go left 7 units. Now, if we're changing the slope, that's because of that a value that's out in front. A is the slope. Now, if a is bigger than 1, it's like making your V shape out of rubber bands, grabbing the top and the bottom and stretching it. It's called a vertical stretch. If it's a fraction between 0 and 1, that actually squishes it. That's called a compression. But we're just going to use it as slope. Now, it's possible that we might have a negative in front of it. If we have a negative in front of it, that means it's reflected over the x-axis. So it's going to go down. Basically, the slope is negative 1. So down 1 and over 1. If it's reflected in the y-axis, we're going to see a negative inside with the x. So remember, this is opposites here as well because of the x piece. A negative outside actually was from the y, so that's reflecting in the x-axis. A negative in front of the x is reflecting in front of the y-axis. So let's see what we can do. Which of the following is the graph of y equals the absolute value of x plus 2 plus 3? Well, I'm going to write this down first, because I want to remember what h and k do. And I do notice, hey, there's nothing in front of this absolute value thing, so that's still a slope of 1. That's still a 1, so that didn't change. It's going to be just as wide as it was before. But this one's a little harder. If this is a plus 2 inside here, where does that mean it went? 2 to the left, yeah. So 2 to the left. The plus 3 in the back is normal. So what does that mean? Up 3. So here's what we want to pick. We want to pick which V shape there goes 2 to the left and 3 up. Which one? D as in dog?
Yeah.
Here's your 0, 0. To the left, 3 up. Boom. There it is. Now notice, all that changed was the vertex. The slope is the same. It's 1 on the positive side and -1 on the left side. This one says, all right, let's try and put a couple of these together at once, okay? Y equals A, absolute value of x minus h plus k. So no more of the up or down thing. That was too easy. I'm going to change it. If there's no number sitting in front of this absolute value symbol, what number is really there? So we're still going to go up 1 and over 1, up 1 and over 1 to the right-hand side of the V, up 1 and left 1, up 1 and left 1 to the left-hand side. But what's important is we now have a new vertex. Where is it? It was at 0, 0 before. Where is this going to move it?
Right.
How about the 1 in the back? Where's that going to move it? Up 1. So we're at 0, 0, and we go 2 to the right and up 1. Where are we at? Exactly. So H and K, that's the vertex for every one of these graphs. We have to be careful that we remember H is the opposite of what we see. Since this said x minus 2, it was actually a 2 that's in there. So here's what we do. We go to 2, 1, and then we check to make sure the slope is still exactly what it was before. Oh, it's a 1 in front of the absolute value. It's still 1. So we'll go up 1 and over 1. Do that several times. And then we do the opposite slope, which is up 1 and left 1 for the left-hand side. And this is our answer. We didn't even have to draw the parent function. Cool. So we have to be able to find a new vertex. We have to be able to look for the number that's in front of the absolute value because that's the slope. Because again, the objective was graph absolute value functions. It didn't say step 1, do this, step 2, do that. We have to come up with that. So step 1 is figure out that vertex, figure out HK. Step 2, see what your slope is. If there's a different number from 1 in that position, then your slope is going to change because that'll be a vertical stretch or a compression. And watch all those pieces at once. Now this one says, let's describe, and let's not actually do the graph yet for this. Let's just describe the transformation. Anywhere there is a number that's been changed from our parent function, remember this is the parent, that number describes a change to the graph. All right. This one says y equals 3, the absolute value of x. And I remember, okay, not only is that the slope, it's also a vertical stretch or a compression. If we take all of those points and we multiply them by 3, are they going to get bigger? That's a vertical stretch. Vertical stretch factor of 3. So it's going to go up 3 times as fast as our normal graph, which had a slope of 1, which makes sense because we go up 3 and over 1, up 3 and over 1. This one says y equals -3 absolute value of x. Oh, a negative. Negatives are for reflections. So this is a reflection over the x-axis. And then a vertical stretch factor of 3. If we graph it, that's going to be taken care of by the fact that we just look at -3 as if it's the slope. So for the right-hand side, we got to go down 3 and over 1, down 3 and over 1. And we're going to see our v is upside down when we do that. All right, this one. Y equals 1/3 absolute value of x. So here's my rubber band. And now I'm going to multiply it by 1/3. Is that going to make it bigger or smaller? Multiply something by 1/3. 1/3 of this distance. Is it bigger or smaller? Smaller. This is a vertical compression. Factor of 1/3. Again, if we graph it, that's just our new slope for the right side. So we'll go up 1 and right 3. That's what we're going to do. So we have to be able to describe them, but yeah, in the end, we want to be able to graph. Take a look at y equals 1/2 absolute value of x. Is that going to go right or left? Is there a number behind the x there? So it's not going to go right or left. Is there a number outside the absolute value bars in the back? Then it's not going to go up or down either. So what really happened to it? Well, the vertex is going to stay at 0, 0 because h and k are 0, 0. When we graph, we use that a value that's in front as the slope of the right side. So I can't go up 1 and over 1 this time. How do I have to go? Up 1 and over 2. And then remember, we do the opposite for the other part of the v, so we're going to go up 1 and left 2. Now here's what I want you to ask yourself. Does it look like they squished that v down? It does, doesn't it? You can see it's much wider than it was before. So that's what a vertical compression does. It squashes it. Squashed down. All right, let's look at this one. Y equals the absolute 2 times the absolute value of x. Look in the absolute value bars. Is this one going to go right or left at all? There's nothing in there, is there, but x. So it's not going right or left. And is there a number hanging out in the back with a plus or a minus? And it's not going to go up or down either. The vertex is at 0, 0. Now all we need is to figure out how we have to move to get our points for our v. How do we move from 0, 0? Up 2 and over 1. Use your slope backwards for the left-hand side. So up 1 and left 2. Now, I want to see if that graph makes sense. So here I am with my rubber bands. And they tell me I have to multiply everything by 2. Does it make sense to stretch it up? Absolutely. Absolutely. Vertical stretch, factor of 2. All right, this little hammer. Has the vertex been moved from 0, 0? No, there's no number in there with the x. There's no number hanging on back. The vertex is still 0, 0. Is there a new slope? Yeah. So from that point, where do I have to go to get my right side of my graph? Down 2 and right 3. And then just do the opposite for the left-hand side. So down 2 and left 3. I told you some of you were even going to be ahead at this point because I saw a couple people that are like this now. Their hands are crossed in front of them because they already did these. They're not going to be incredibly hard if you just remember, look for HK, where's the vertex, and then use the number that's in front as the slope. Oh! We did leave some for tomorrow. That's good. I left a little bit for tomorrow. Not a lot, a little bit. Want me to make up another one? You got them?
Yeah.
All right then. Huh? You don't need me anymore? I love it when that happens. Remember, don't make any stinking tables. Do not use a table of values for 9 through 15. The instructions are going to say, make a table of values. Don't make a table. You're just fine without them. And remember, if you want, quick squirt of hand sanitizer and then, grab some graph paper, it'll go faster. If you're not making your own graphs as you go through that. That's